All right, the second part of week 6 is chapter 14 and air pollution. So let's get some fundamentals out of the way. First thing, air pollution can be both natural and anthropogenic, or man-made. For instance, trees emit something called volatile organic compounds, and that is what is called a precursor to ozone. Soil and lightning emit what are called nitrogen oxides, and that is also a precursor for ozone. So those two together can actually make ozone, and it's an entirely natural process. On the flip side, there's plenty of other things that are man-made that also create pollution. So just know that pollution can be both natural and man-made. Second thing is there's two types of pollutants that we talk about. First is primary, and that means it's emitted directly into the atmosphere. So for instance, those trees emitting VOCs, that is a primary pollutant that exhausts out of your tailpipe. The carbon dioxide, carbon monoxide, and the nitrogen oxides that come out of your tailpipe, because they're directly from the source, those are primary pollutants. The fine particles from a smoke, from a fire, would be another example of primary pollutants. There's also the secondary pollutants. Those secondary pollutants are created by reactions in the atmosphere to create different pollution. So the best example of that is ozone. Ozone is not emitted anywhere. It is created in the atmosphere by combining nitrogen oxides and VOCs in the presence of sunlight and heat, and that creates ozone. And so ozone is a big deal. Ozone is a significant pollution, significant pollutant, especially along the East Coast and in California. But it is a secondary pollutant, meaning that it is formed not directly from someplace, but it is formed in the atmosphere. So primary, secondary pollutants, there's both natural and anthropogenic. The other fundamental thing to talk about is the air quality index. Air quality index goes from green to yellow to orange to red to purple to maroon in increasing severity of health impacts or decreasing air quality. I want to point you to page 443 in your book. There is a color coordinated table of the air quality index. It's actually terrible. It doesn't actually adequately color the indexes. Those colors that I gave you are the true colors that should be represented in those in the air quality index. Green is good. Yellow is called moderate. Orange is unhealthy for sensitive groups. Red is unhealthy for everybody, and so on and so forth. So just want to point those out. That's a good fundamental start to air quality. Okay, so let's talk about a smokestack. What happens to the smoke, the pollution that comes from that smokestack once it comes out of it? Your book does a pretty good job of describing this in good detail, but I just want to go over a real topical real quick. So that pollution comes out. It is immediately impacted by the atmosphere. The wind is probably the first thing to consider. If the wind is not blowing at all, that smoke just rises and doesn't do anything. Just basically stays together. If the wind is blowing, especially if it's blowing really hard, that smoke does something called disperse. And what it is instead of think of it in this column of smoke, the smoke spreads out. And because it's spreading out, the concentrations of pollution go down, which means that the health impacts aren't as great. So higher wind speeds mean lower impact on the air quality, or healthier conditions overall. And that's because the wind helps to disperse the pollution. The next thing to consider is the temperature profile. In stable conditions, under high pressure, you have clear skies, and you get something called a subsidence inversion, or at nighttime you get that inversion, that nocturnal inversion. Whenever you have an inversion, the atmosphere is stable. When the atmosphere is stable, it traps that pollution from escaping into the free atmosphere. So into the free atmosphere, the concentrations of pollution go down quite a bit, and we typically don't worry about that. But when the atmosphere traps it underneath that inversion, because that inversion doesn't allow rising motions, so it traps all the pollution that's emitted below it to accumulate. And that's when health can be incredibly impacted. because the concentrations can increase and increase and increase as long as that inversion doesn't break. And your book actually provides a story where people died from in this situation where the inversion trapped a bunch of pollution, and people end up getting sick and dying from it. That aside, okay, so we can, the wind will disperse it. Lack of wind will certainly not help pollution levels. And then if you have stable conditions in the atmosphere, it can trap that pollution near the surface. Why is that important for, say, industry? This is anybody going into engineering or consulting. This is something to keep in mind. The stack height, or however tall your smokestack is from an industry or a factory or a power plant, will impact the health of your citizens that are around that. The higher up that smokestack can get, the less likely that pollution is to be trapped near the surface at night under the nocturnal inversion, or during the summer months when you have a subsidence inversion, because the smokestack actually climbs up above that inversion. It's amazing in meteorology how just a couple of meters makes a huge difference on what the sensible weather is like. And air pollution, just a couple of meters higher of a smokestack, might get that pollution up above that nocturnal or that subsidence inversion to help disperse that pollution and not affect people's health. So release height matters, and then in terms of what happens to air pollution when it comes out of the tailpipe or the smokestack or wherever, it is the speed, the wind speed, and then whether or not the conditions are stable to help trap that air pollution near the ground. Topography plays a huge role in air quality. The reason is mountains can trap pollution in valleys. This is incredibly important in California, not to the same degree, but important in places like Salt Lake City, and also important in places like Maryland, where the Appalachian Mountains can actually help trap pollution a little bit closer to the surface, because subsidence coming off the mountains heats the air up as it comes down. Heating of the air may actually cause a subsidence inversion, and that subsidence inversion can then trap that air pollution near the surface. Any picture that you look at, say California, the San Fernando Valley, if you look at pictures from the mountaintop, you'll actually see a level where you don't see that brownish smog anymore. And that's because that's above the inversion. Those mountains are helping to trap that pollution in the valley, and the subsidence inversion that develops across the mountains, and or just an inversion in the environment itself caused from high pressure, whatever the case may be, will actually just trap that, and right above that we'll get into beautiful air. I saw this especially in Utah when I climbed up to the Wasatch Front. That's the mountains right next to Salt Lake City. You can climb up to a certain level and you can look straight through the top of the pollution at the top of the inversion. And then once you climb above that, the air is incredibly clear. Your sinuses clear out. It is amazing how that works. So topography is a huge influence on air quality, and your book talks about that pretty well. And I just wanted to introduce that here.